Okay.
Metti la prima slide. Eh? Ah, no, mi serve la prima slide. Ho cambiato un po' il titolo. Okay, so welcome back, and it's my pleasure to introduce you Professor Larry Davis from University of Maryland, and now he is a consultant with Amazon. And Professor Larry Davis is very known, so I will skip his biography, also because we are a little bit late with the time. So he will talk us about AI and computer vision at Amazon Fashion. Please, Larry.
Okay. All right, Cosimo, thank you very much. I really appreciate the opportunity to talk to the conference this morning. My only regret is that I'm in Seattle, Washington, in the overcast, rainy conditions you get here in the Pacific Northwest, rather than with all of you in sunny Italy. All right. So I'm going to start by telling you a little bit about how I got into computer vision. The reason is that this year is the 50th anniversary of my joining computer vision. So we can go to the next slide, please. All right, so I was a professor at the University of Maryland. I'm still a so-called College Park professor, but I'm not really materially involved in any of the work ongoing at the university right now, but I was there for a long time. I was director of something called the Center for Automation Research, and that was the home to what's called the Computer Vision Laboratory, right? And that lab was established a long time ago, way over 50 years ago, by Azriel Rosenfeld, who was my advisor and was also one of the founders of the field of computer vision, maybe the founder, right? Azriel was a bona fide genius, right? And so it's still one of the US's largest computer vision research labs. During my career at Maryland, I had the privilege to advise more than 75 PhD students, and incredibly, 20 of them are current Amazon employees, which goes a long way to explaining why I ended up at Amazon when I decided to leave the university rather than somewhere else. Okay. Somebody put a note up on, should we also see a slide currently, Cosimo? I'm not sure if that person is having a problem via Zoom. All right. Towards the end of my career at Maryland, I worked with a couple of my PhD students on fashion-related problems, and I wanted to see some of these ideas impact customers at scale. And to do that, I thought that Amazon was going to be one of the best places to do that work. And so I joined it. Next slide, please. All right, but so how did I get started? I mean, when I was an undergraduate, right, this was a long time ago at this liberal arts college called Colgate University. It's in New York State. There's a picture of it, a very beautiful place. And there was no undergraduate computer science really anywhere in the United States, maybe one or two programs, but certainly not at a small liberal arts college. But I was lucky enough to have a physics professor who was really smart, and he saw that computer science was going to be the future. All right. And so he encouraged me to take a reading course with him, and he introduced me to two giants, early giants in the field, Marvin Minsky, who probably all of you remember, the founder of the AI lab at MIT, and one of the earliest roboticists, a brilliant mathematician, Michael Arbib, who is, I think, still active at the University of Southern California. So they had written some books. Minsky wrote a book on automata theory, is really what it was about, the theory of computation, which is what he did before he got into AI. And Michael Arbib had written this very approachable book on the relationship between brains and machines and mathematical modeling. And this got me really interested and convinced me that rather than being a mediocre mathematician, maybe I could be an above average computer scientist. Next slide, please. Okay. So I went to the University of Maryland. I was there actually until 1977. So there's a little typo on the slide. And there's Azrael on the left, right? And he built up a pretty big lab and had, of course, as my advisor, a huge influence on my career. And the other person that had a big influence on me was Stephen Zucker, who is also a brilliant researcher interested more in the intersection of human vision and mathematical modeling of vision systems. Stephen is now a chaired professor at Yale, but I learned a tremendous amount from the two of them. Go on to the next slide, please. Next slide. All right, then, and really my first day in Azrael's lab, which was early September 1972, he gave me a stack of papers to take away and to read. And he said, well, read this one first. I don't know how many of you are familiar with this paper. It's actually one of the most famous papers in the history of science, right? It's called What the Frog's Eye Tells the Frog's Brain. And it really revolutionized, not at the time, people really rejected the philosophy in this paper, but it revolutionized the way that we think about vision systems, especially early stages of vision, not as just hardware that finally replicates an image of the world somewhere in the brain for subsequent interpretation, but the world is represented in terms of a set of features that have ecological importance, right? And the authors of this paper, there's a picture of Jerry Lettvin there, Lettvin, Maturana, McCullough, and Pitts. I mean, these were four of the leading scientists of the time, right? McCullough and Pitts had written this famous paper on really on automata theory, one of the first papers on that subject. McCullough was this amazing genius, was a medical doctor, a mathematician, a philosopher. I mean, it was just an amazing intellect. Pitts was one of the foremost mathematicians of his time, although he was an alcoholic. So you should really, if you've never read this paper or seen it, it's a landmark paper, and it's all about the fact that the fly's vision system has evolved so that it can eat and escape predators, eat prey and escape predators, and they interpret the responses of single cells in the ganglion of the frog, and they were able to make these measurements because Maturana, that was his specialty, these single cell recordings. They could see the types of dynamic patterns that these cells responded to and can understand their relationship to the survival of the frog. Next slide, please. Next one. All right, so my dissertation was about a whole bunch of topics that nobody cares about anymore. Detecting symmetries in planar shapes, methods for piecewise approximations of planar shapes. Computing power was, to say the least, at a premium. Digital images were at a premium. It was very difficult to get an image digitized so that you could perform any types of operations on it. And Azrael put a big premium on publications. That was very important to him. So as a PhD student, I had 19 journal publications, one lousy conference publication. It was really a very different world to do research in then than it is now. Next slide, please. When I finished my degree, I went to the University of Texas for 4 years, but then I returned to the University of Maryland in 1981. And so this is kind of the last slide of any substance of historical interest, because the 80s were really interesting in the United States to do research on computer vision. And the reason was that in the early 80s, Japan announced their so-called fifth generation computing project, right? They were going to be building the world's largest supercomputers. And this caused some alarm in the United States because they were worried about falling behind in the race to generate supercomputers. So the major funder of large-scale computer science research in the US was the Defense Department, in particular, the agency called DARPA, the Advanced Research Projects Agency of the Defense Department. And the person on the left, Clint Kelly, was the one who directed the AI part of this strategic computing program. And it really combined two things. It combined the development of a new generation of parallel supercomputers and then certain very hard AI problems. And the hard AI problem that we were involved in at the University of Maryland was autonomous navigation, self-driving cars, all right? And the types of supercomputers that were developed under support of that program with things like the connection machine. That's the picture that you see of this very aesthetic device on the right-hand side of the screen, right? And the connection machine was the largest scale parallel computer in the world at the time. It had 64,000 very small 1-bit ALUs on it. And in order to get them talking to one another, it had this very complicated and expensive interconnection network based on a hypercube connectivity pattern. And in fact, the connection machine was designed by a guy named Danny Hillis, who was a student of Marvin Minsky at MIT. And they started this company called Thinking Machines. And Thinking Machines was the first Google-like company, except it was an abject failure in the sense that they had personal chefs and an amazing campus, right? And working there was a privilege. Feynman, the very famous physicist, worked several years at Thinking Machines on various components of this connection machine. All right, so this autonomous navigation project was headed by Carnegie Mellon, by Chikeo Kanade, CMU Nav Lab. And it's interesting that almost 40 years ago, the most successful computer vision model that was used to drive this truck was a neural network. A guy named Dean Pomerleau was one of Chikeo's students, and Dean designed this really MLP, this multi-layer perceptron that learned to drive the so-called Nav Lab. And if you read Dean's PhD thesis, you'll see that it includes a lot of themes that are current and important today in the sort of second or third deep learning area, right? And it was very difficult and expensive to collect real data. And so they did a lot of synthetic data generation and data augmentation of real data. So they trained their model on synthetic data and then fine-tuned it with real data and had to deal with domain adaptation problems, really very, very modern. My own student, Mark Rosenblum, developed a comparable road following algorithm. That's what this did. It followed simple roads based on some work that was coming out of Tommy Poggio's lab at MIT on using radial basis functions to build neural networks. So certainly these things didn't have the computational power behind them or the architectural details of modern, convolutional neural networks or transformer neural networks. But it is interesting that 40 years ago, these types of, at the time, large-scale neural networks were the most successful computer vision models for these difficult tasks. Come to the next slide, please. Right, well, we want to get to Amazon in a hurry, so we'll do the next 30 years in 30 seconds. In the 1990s, mostly worked on problems in human activity recognition and video processing. We got a large amount of money from the Keck Lab, from the Keck Foundation in the US to build a synchronized 64 camera laboratory in our building so we could take multi-view video, synchronized multi-view videos of people in motion. In the 2000s, especially after 2001, there was a lot of research support to work on visual surveillance that goes on through today. And then in the 2010s, whatever they're called, we did a lot of work in the lab on related to faces, face recognition, media forensics, determining whether an image is authentic or has been manipulated in some way, and then the work in fashion, which gets us up to just a few years ago. So please go to the next slide. Okay, so what's it all about at Amazon, right? Right, at Amazon is not like, you probably all know this, it's really not like Facebook and Google. It's not a research forward corporation. There's a ton of research that goes on, but everything is driven by problems that our customers are having, especially in the retail area, problems our customers are having in shopping on Amazon.com. And then we work back to the science and engineering needed to address that customer-facing problem. So the principles that guide our work is that our solutions have to be good for all our customers. So Amazon Fashion is for everybody. We want to provide the best shopping experience for all of our customers all over the world, all right? And those customers are very diverse in their ethnicity and their backgrounds, their tech savviness, right? And we need scalable solutions that work for our entire catalog. I'll tell you in a minute how big that catalog is, right? So for all our catalog, for all our customers, and with no discernible perceptual latency in the delivery of those services. Next slide, please. All right, so one of the biggest problems, so we call them pain points, right? What makes our customers unhappy? And there are a lot of things that make them unhappy, right? You've all shopped online. It's not the most pleasant and seamless experience that you can encounter, all right? So discovery, how can we help customers find products in their price range, of high quality, and their size, that's relevant to what they're looking for, relevant to what we call their shopping intention, okay? So the Amazon catalog, the clothing catalog, is enormous, right? In fact, it has close to 1 billion items. We call these items ASINs, all right? They're the individual clothing items in the catalog. And the catalog changes at very high velocity because there are designers and manufacturers all over the world that are trying to create new designs and grab their share of the global clothing market, all right? Each of these ASINs is typically sold by multiple sellers, all right? So you might have a situation where some manufacturer manufactures some item in their factory, they sell it themselves, but they also sell it to other people who then in turn sell it to customers on Amazon.com, right? So these multiple sellers independently set their prices and compete for what's called placements during customer search, all right? That customers will see their particular instance of the item, right? And the most common entry paths for customers into catalog are text-based search, all right? There's also a secondary path, I'll show you a slide in a moment, called street to shop, that allows customers to find items in the catalog through images. But the overwhelming majority of customers, when they're looking for something on Amazon.com, open Amazon.com and type some text into the search bar. Next slide. All right. So here's just one slide. You can read this paper if you're interested, that explains how visual search works. In 2022, there's no rocket science here. I mean, some customer finds a product that he or she likes in social media and wants to find it on Amazon. So there's an Amazon app, it's called Style Snap, where you can input an image, and then what does the computer vision system do? Well, no surprise, it has to solve a segmentation problem to find the different items in the image. It constructs visual embeddings of those items, and then it matches them to the catalog, right? So the main challenges are, of course, the segmentation problem in natural imagery, right? Especially because if you look at these images on the right, if for some reason you're interested in the blouse, there's only partial information about the blouse because it's hidden by the jacket, right? So that's a real challenge. And the domain mismatch between the outdoor imagery typically, or even indoor, taken under certainly non-studio like illumination conditions, and the illumination of the products that you have in a catalog, which are almost always shot in a studio with highly controlled diffuse illumination, right? So a lot of the details about this so-called Style Snap application are described in this archive publication. Next slide. All right. Confidence in making the right purchase, right? So customers want to see high quality products, lots of positive and relevant reviews, informative customer review images, brands that they trust, high keep rates, meaning items that customers don't return too often, all right? And here there's a problem. This is a common problem in any retail organization having to do with so-called cold start products, so that when a seller introduces a new product into the Amazon ecosystem, you know, how do we rate it, so to speak? How do we compare it to products about which we have a lot of information so that we can show it to customers in a way that will maintain their trust, right? If you've ever shopped on Amazon.com, then you might encounter a situation where you find some product, you see the image, you like the product, you go to the so-called detail page. We'll see an example in a minute where all the product information is there for you to look at. and then you discover they don't have that product in my size. Okay, and so what do I do, right? So customers want to easily find substitutes for products not available in their size, or maybe something is too expensive. You don't want to spend 40 euros on that polo shirt, but is there anything that looks like that in the catalog that you can find for 20 euros? All right, so next slide. All right, so this problem of product substitutes is a big problem for all retailers, right? So suppose you find an item that you like, but it doesn't really suit you, not available in your size, too expensive. So we should be able to help you find items that look like that. And of course, what makes this difficult, I mean, this is, again, all of you knowledgeable about computer vision, you can see immediately how to go about solving a problem like this, right? The images of relevant products will be different. You can't do any kind of trivial direct image comparison using classic computer vision-like techniques, right? You might, the product will generally be viewed on a different human model, and the pose of that model will be different than the one in the product that you're interested in, right? So how do you solve this? You use deep learning to construct product embeddings, right? Visual embeddings of those products, right? They basically come down to compressed representation so that images of similar products get mapped to nearby locations in the embedding space, all right? People have looked at this problem ad nauseum. There are no shortage of publications on how you do your sampling, right? So that for various loss functions, you can get the kind of hard negatives that you need to really get good structure in the underlying embedding space. If you're interested, we had one admittedly small contribution to this problem that was published in a workshop at ICCB a couple of years ago that used the product descriptions to compute an adaptive margin for the triplet loss, right? So it facilitates identification of hard negatives, right? For those of you, who have some experience in retrieval, you know what all this means. We go to the next slide. All right, so here's a product detail page. This is an example of that visual embedding. We call it visual similarities at work. And so there's the product you're interested in. And it comes in a couple of colors. You can, if you look at the upper right-hand side of the screen, you'll see that the prices range from, what is it, $9.99 to $15.99. Customers find this very confusing, right? Usually, if you go into a brick and mortar store and there are several versions of the same product, the prices are the same, all right? I mean, it's one store, they have a price for that product. But because we have so many sellers selling the same product, you can get very, very large price range. Customers hate this stuff, all right? It really annoys them. Because you see the product that's advertised at some price, but then when you look at some color variant and in your size, all of a sudden the price is like 2 times more than the price that you saw in search, and you get really pissed off and you leave Amazon.com and go shop somewhere else. So this is a problem, not a computer vision problem that we end up dealing with. But what you see at the bottom of the screen is a so-called widget. That's what they're called internally. And this is the result of applying this visual similarity model along with a ton of business logic that makes sure that the products that we end up showing are good products that have large numbers of reviews, right, small return rates, whatever, so that when if customers see any of these and are interested in them and click on them, they'll get pushed through to detail pages of what we refer to as good products. All right. So if you shop on Amazon.com, you'll see this, and it's really nothing more excuse me, than these visual embeddings that you're all familiar with. Next slide, please. All right, so customers also want to understand how to complete the look, right? Lots of papers in the computer vision literature on building outfits, right? How to wear an item will match with other items they already own. So what shoes and handbags go with a specific dress ASIN, right? And at Amazon, we call this wear it with. If you shop for clothing on Amazon, most detail pages will have a widget. The widget doesn't always show up because there's competition for widget space between different ways of trying to show you other products, but it shows up a lot, right? It's called wear it with. You can go to the next slide. All right, so wear it with, the model that's close to the one in production is actually described in a paper published last year in a CVPR workshop. All right. What it does is it constructs an embedding space that, rather than capturing visual similarity of products, captures stylistic consistency of clothing items, right? So each product is represented at some point in this embedding space. As you construct an outfit, this constructs it sequentially using a recursive model. Outfits are also represented as points in the embedding space. And product types themselves, shoes, tops, whatever, also have representation. So this is a language-like model as points in the embedding space, right? So the intuition is that as you're building an outfit, when you add a product type embedding, you want to add a shoe or a purse, right, to the embedding of an outfit under construction. This addition, which isn't a simple addition, it's done by some recursive network node, moves you to an area of the embedding space that will contain items from that new product type that complement the outfit, right? Go to the next slide, please. All right, so let's see. I worked on this problem with one of my, I'm trying to keep track of the time here, one of my students when I was at Maryland. So what's the difference between solving this problem at Amazon and solving this problem in an academic setting? Well, in an academic setting, why is the problem even interesting? Okay, I mean, why does anybody work on this problem? And one reason is that this is a set recommendation problem, right? And this is a relevant interest of the problem. I'm not recommending a single item, but recommending a set of items that in some sense go together, right? So how do you capture this notion of set element consistency and then efficiently construct sets from some universe of items that are good sets, all right? But in Amazon, we have other constraints over and above trying to solve this interesting academic research problem, all right? And one of them has to do with diversity, all right? So across the set of items, so when we take a single address, we want to build outfits around a dress, all right? If two items are visually similar, then their wear it with embeddings are going to be similar too. There's no way to escape that, right? And so if you use a simple model like beam search to build multiple outfits, you start with a dress and then you say, okay, I'm going to put shoes in next. And so you construct the embedding of shoes conditioned on that dress, all right, and the representation for shoes. And you go to that part of the embedding space and you start retrieving shoes. And if there are a lot of shoes that look alike, there's one which is the best match according to the model, and then the ones that are going to be second, third, fourth, fifth best match are all going to look remarkably like the best match, okay? And so you'll end up generating outfits that don't have any visual diversity, all right? So you need to overcome that because it's not going to be a good experience for customers if you recommend a set of visually indistinguishable outfits to a customer, even though each of the items in the outfit are somewhat different, maybe in terms of price or other characteristics. They all look the same. Additionally, you need to have some diversity over all the outfits in the catalog, all right? So some items, they just go with everything, right? They're easy to match. And you just, so they'll give you really high scores for the quality of outfits, right? They're going to go with a lot of things. But this is really boring for customers if every time Amazon shows them an outfit, we use the same items over and over and over again, right? And the other thing is that outfits drive sales. And if you use any single item in too many outfits, it will go out of stock pretty quickly, all right? And then that's a bad experience for customers. In fact, when an item goes out of stock, we have to sort of take the outfit down from the website. And so now we're down one outfit and have to go and create more, which is an expense, okay? So there are just, lots of other factors that need to be taken into account in order to build and maintain a large set of outfits. And then there's a visualization problem. How do you show customers the outfits? Ideally, we would be masters of virtual try-on and would be able to take the product images of all the elements in the outfit and create a real-looking instance of the complete outfit on a model. But we can't come close to doing anything like that. That's really hard, all right? And so, finding products, the products that go into making outfits, therefore, have to be, the images we have of those products have to be usable in some type of aesthetic visualization of the outfit. So that's another constraint on products that we can use for outfits. I keep trying to get somebody to work on the problem of what I call virtual takeoff. That's, you have an image of a product on a model, and you'd like to create a plausible image of that product, say lying flat on a table, or some other type of canonical view, so that you can use it in a visualization of outfits containing that product. Next slide. All right, so this is the architecture of that outfit builder model. All right, so I said it's an RNN. I'm gonna, I mean, we sort of talked about this. Click once, please, Cosmo, because there's one animation on this slide. All right, so just click it once. Or maybe it's already on there. Okay, so I said all this, right? The RNN just updates an outfit embedding. You input the representation of the next product type, and the RNN then updates its representation of the outfit so that you can search for relevant instances of the next product type. Let's move on. Next slide. So I'm going to go through these really quickly because I want to get to some of the other topics. All right, so CVPR this year, a paper on using transformers instead of recursive networks. There's absolutely nothing surprising about this, right? In 2022, this is kind of almost a turn the crank exercise. All right, you know, why use a sequence model when you can use a transformer? I mean, we all know that the shoes you choose are driven by the purse more than they're driven by a scarf. So why are we letting the recursive model munge up the representation of the scarf and the purse when what we and the shoes when what we really need is to focus our attention on those shoes or a belt or something else that are more critical to choosing the right purse. So we have this transformer model. You might recognize Gerard's name here. All right, so Gerard was participated in this. So let's just quickly run through these because we're up to 4:41 your time, and I know that we have to end this by 5 your time. Go, next slide, please. All right, okay, so let's skip this. All right, next slide. All right, and the next slide. We're not going to talk about this. One more. Oh, I see. I thought I had blanked all these slides out. They were hidden in my original presentation. Next slide. All right. So the outfit transformer does two things. There's actually two models. First, we train a model using a transformer architecture that outputs a compatibility score that allows us to rank outfits. All right, what's the next best outfit? And that essentially is used as a pre-training exercise to build the transformer that completes outfits, that extends outfits. So given an outfit containing K items and some relatively arbitrary description of the next item you want to put into the outfit, the transformer will output an embedding of that item that you can use for search. All right, so let's go to the next slide. All right, okay, next slide. So that's the standard transformer architecture. No surprises here. Keep going. I just want to get up to some of the examples here. Again, it seems when we transferred the PowerPoint presentation, all my slide hiding disappeared. Okay, all right, keep going. I'm going to flick through these quickly. Again, skip, skip again. Again, just skip it. Sorry about this. All right. So a little bit about experiments, right? So these are experiments used in academic papers where really don't have the capacity to have large numbers of specialists look at outfits and rate them. So there's a fill in the blank. It's really a multiple choice, a scoring model, and then a recall model where you show the model K-1 out of K elements in an outfit, and it has to rank all the items in your repository, in your catalog, as being the next. We need shoes to finish this outfit in this example, and then you measure recall at top K. All right. Now this is really the fill in the blank model is not too interesting because it's not really a scalable solution. You have to actually score each one of the items, and you can't do that against the real catalog. And the recall is also not a very useful practical metric because when you look at, for example, the shoes recalled here, it's certainly not clear to me that any of the ones that come out before the actual shoe that was part of the testing outfit, whether those items are really not as good, if not better, for completing that outfit than the one that happened to be included in the test set outfit. I mean, at Amazon, what we do to really evaluate these things is we have an army of what we call fashion specialists, and they look at the outfits that are generated and score them for us. And we take into account the subjectivity, that is the disagreement amongst people in these types of subjective analyses. But that's impractical to do in an academic setting. So we do simpler things, right? Next slide. All right, so this is a bunch of numbers, right, that show that this transformer model performs better than previous models. The one that performed the best of previous models was another one of our papers that use subspace models, and it was a powerful mechanism, but it turned out to be both at training time and inference time a more expensive solution, and one that wasn't really practical from a production point of view. But this makes the transformer model makes improvements over that model nevertheless. Next slide. All right, so we're going to skip this one. It's too small anyway. Skip this one. So just you might have seen, I mean, other models do things like this, that in the model, when we want to add the next item, we could add a natural language description of that item. So here it says add a coat in a neutral color like beige, cream, or light brown. And because our repository has not only images, but has product descriptions, we can combine the image and text representations of products and do this type of text-based retrieval of items. I don't just want a coat, but I want a coat in one of these colors. Next slide. Right, there are just more examples of being able to complete an outfit through some text-like description of what you want the next item to look like. Next slide. More, too many. Next slide. No, this should have been gone. Go to the next slide, please. All right. Another big problem, fit. What size should I buy, right? So returns due to fit are a large pain point for customers, all right? So this is, kind of a classic collaborative filtering like problem. What makes it challenging practically are things that are not too interesting from an academic perspective. One is, if you go to the Amazon catalog, you'll notice that the sellers use endless variations on size strings when they describe their products. So XL, extra large, X large, it goes on like forever. And this is just the nuisance variable, so to speak, in trying to relate products of different sizes to one another, so that a product from one manufacturer in an M, in a medium, would correspond to maybe a large from some other manufacturer. And just the fact that there are this just menagerie of strings is a problem. All right. There are it's very typical online shopping to have a family to have one account. And so you don't really know who's buying for who. All right. So if you're trying to put together purchase history information to make a good recommendation for a customer, well, maybe the last 3 pair of shoes they bought were for their kids, and now they're looking for a pair of shoes for themselves. And if you use the history of shopping for kids for them, you're going to make ridiculous recommendations, right? So, and even shopping for kids is problematic because somehow Amazon ought to understand that your 4-year-old is bigger than he or she was when she was 3. All right. And so doing size recs, you need to have some kind of understanding of growth patterns of children. Next slide. But the part of fit that brings in computer vision in a fundamental way is, rather than picking a size, maybe we can make an item of clothing specifically for you, right? So, it's generally very expensive to have items made to measure, made for you, all right? You can do this on Amazon. There is the product is called Made for You, and you can get a t-shirt made for you, right? Clothing made on demand, right? Clothing manufacturing introduces a tremendous amount of pollution into the environment. And at the end of the year, the end of the fashion year, a lot of clothing that was manufactured goes unsold, right? And it gets disposed of in one way or another. Some of it gets sent to people who can't afford clothing, but the majority of it just gets burned or something, all right? And so if I want to make a piece of clothing specifically for you, then I need to know about your body, right? I need to know about your 3D body shape, all right? And if I want to show you what this t-shirt that I'm going to make for you is going to look like on you, then I also need to solve a sort of virtual try-on problem. So the made for you product, if you go and try it out, it'll show you what the t-shirt will look like on your body after you submit your images. And you can then actually style the t-shirt. How long should the body length be? What neckline do you want? What sleeve length do you want? So basically the equation is that a 3D body model, which you need through computer vision, plus some three-dimensional model for the garment, which is problematic, all right? And a physics clothing engine taking a classic approach and a rendering engine will give you an image of the customer, yourself wearing the garment, and eventually, because you can derive the measurements from the 3D body model, the actual garment will arrive at your home. Next slide. All right, so Javier Romero, when he was with Amazon, worked on this 3D body modeling problem, all right? And there was a paper at ICIAP 2019 that describes what he did, right? So how would you solve this problem? You say, well, I bring a bunch of people into a lab and I take pictures of them. There's one on the left and put in front of a natural background. And I scan them with some type of a 3D scanner and use that as training data in order to train some kind of a deep network to predict that body model from an image, right? So, so this is like depth from RGB, right? And there's an example on the right, and it looks pretty good, all right? But if you go to the next slide, when you look at the recovered shape by displaying its surface normals, you see that it's very rough. All right. Even though the depth computed on average is very accurate, the surface is just not smooth. And this leads to large errors in estimating the body measurements that you need for manufacturing, right? You can think of a tape measure that it's like a fractal surface, right? It has to go over all these little bumps and valleys, and you end up, you can smooth it a bit, but you end up with errors in these measurements. And the measurements have to be pretty accurate if the t-shirt is going to fit you comfortably. All right. And so this was a key insight that Javier made. And so the paper describes the network architecture that he developed for recovering the surface normals rather than directly recovering depth. So the next slide shows some examples. Right. So you can see that the pink are the recovered depth maps, some of which are very bad. And the green are the recovered normals, all right? And so this model combines segmentation loss because we want to make sure we get all the body pixels, and then this loss on surface normals, all right? And again, the details are in this paper. So let's move on. All right. And so the 3D virtual try-on, when you actually see this item on yourself, I mean, you could solve this problem with a classic cloth simulation. So we have the 3D body model. Since we manufacture the t-shirt, we know what the sewing pattern is. We know what the material is. So we know the material properties. So we could get some off-the-shelf industrial grade cloth simulator, and we could run the simulation, then render it and show you what the t-shirt will look like in your body. But the problem is, it's too expensive computationally, all right? And so we developed a solution based on deep learning. We're still in the process of trying to get permission to publish this, so I can't tell you much about the actual solution. I'll give you a reference where you can read it. But basically, we train this deep learning model with lots of synthetic data created using this this physics-based cloth simulator, and that gives us essentially an approximator to the physics-based cloth simulator that runs in real time. All right. If you want to try it, you can try it by going to Merch by Amazon. So Merch makes well over 1 billion T-shirts a year. Customers submit graphics patterns, and then Merch makes the T-shirts for you. So maybe Cosimo wanted to give everybody a T-shirt with some graphic on it, it's a logo of the conference, right? He could go to Merch and submit that graphic, and Amazon would ship him a few hundred T-shirts, okay? But you can go to Merch and you can buy any of the T-shirts that other people have designed and try them on your body, all right, in fixed sizes, right, to try to find the one that will fit you best using this deep learning approximation to cloth simulation. All right. I think since we're at 5:54, Cosimo, what do you think I should do? Should I wrap up here? I don't want to impinge on people's time.
Keep going. In 5 minutes left.
Okay. All right. Okay. So let's go to the next slide. All right. So this 3D virtual try-on requires knowledge of three-dimensional models of the clothing, sewing patterns, material properties. And so you really can't scale this to something like the Amazon catalog. So can we create a try-on experience that only requires the image from the catalog for the item, right? So this is, the virtual, the type of virtual try-on that's familiar to us in the computer vision community, right? And so we also have a program on, we call it Paper Doll, all right? I didn't come up with that name, somebody else did. Paper Doll virtual try-on. So next slide. All right, so 2D virtual try-on, the idea is you have the customer submits an image, we have some catalog images, and what we'd like to do is we'd like to put all of those clothing items onto the customer image, and we'd like the result to be indistinguishable from a real image, so the customer really gets the look and the look of what that outfit will look like on her. Next slide. All right, and so again, there's a paper last year's CVPR that describes one of the models that we developed with this virtual try-on. All right, basically, the deep learning approach has a shape network which constructs. So you have as input, you have the image from the catalog, as well as a automatically computed segmentation of that image into skin, top, bottom. There is a customer image which gets segmented by some deep network. Those two things get combined by what we call a shape network that gives us the target segmentation for the output image. All right, and then we also encode the appearance of the different items that are going to be in the final image, and there's an appearance network that maps that onto the target segmentation. But that appearance network has a very hard time capturing the fine detail, the patterns, the higher frequency details from the catalog image, and so we have an iterative step that essentially fine-tunes the appearance network in order to get a better rendition of the garment on the customer image. And what allows us to do this, go to the next slide, please. Yeah, so this, the next few slides, click back and forth, is we can also generate the result for the catalog image itself, and we'll get the same type of degradation of the high frequency detail from the catalog image, but we know what the catalog image should look like. So we can go through this little cycle of activity where we fine tune the appearance generator so that we recover the original catalog image. And because of that, we also recover a much more accurate version of the customer image that we're trying to generate. All right, so click through a few slides. All right, so time goes by. All right, we get a better version there, okay? Here's a bunch of examples. Let me just say quickly that what I just described to you is academically interesting, is completely impractical, because what it means is that you have a different network for every garment, because you have to go through this fine tuning to learn how to change the appearance network to reconstruct, you're essentially overfitting to that particular pattern. and you just can't practically maintain a different network for a catalog as large as Amazon's for every item in the catalog. Next slide. Just some more examples. Next slide. Keep going. All right, so I'm just going to show examples here. We're also interested in reposing people for a variety of reasons, right? Like increase the diversity, the appearance of models that are displayed on our detail page. So last year's ICCB, we had a paper on reposing. It was called SPICE, Learning Realistic Human Reposing, a very complicated paper. So we're just going to flash through these to the results. Next slide. All right, keep going. There's some videos here, but we're going to see them later anyway. All right, so what SPICE basically does, it doesn't require paired data. So by paired data, I would mean that during training, you would have the image on the far left, that would be the source image, and you'd have an image of that same person wearing that garment in the target pose, so that when the network generates its approximation to that, its prediction of that image, you can actually see how it compares to the actual image of that person in the new pose. But we don't have that type of paired data. Even for Amazon, that's fairly expensive to acquire. And so we need an approach that doesn't require it, all right? And so the key idea here is to do some 3D body recovery, some 3D model recovery, right? So that this thing can be self-supervised, all right? So go on, because I'm just going to show the results and then come to the end. Now, next slide. One more time. Again, next slide. Next slide. This is more internal. This is the network is very complicated. Next slide. So here are some results. You see the source and the target. Sometimes these are like zoom in, sometimes they're pose changes. And then the right-hand column is the synthesized results. So that it worked remarkably well in predicting the appearance. Even the faces look like plausible side views when all you have is the front view of the face. Next slide. And you can, there's videos here. If you can play the video, if you can find it and play it, do it. If not, we'll just skip to the conclusion. No, okay. There are videos, you can find them on the webpage. All right, so in conclusion, Amazon provides a pretty unique environment for building new computer vision systems and deploying them that impact millions of people and that require some fundamental science breakthroughs. And when I recruit new scientists, I point out that you might come to fashion, but within Amazon, there are a tremendous number of other opportunities to work on hard computer vision problems in other parts of the corporation. All right, so I want to thank you for your time. Sorry, I had some problems with the logistics in Zoom, but if you have any questions, or even better, if you're interested in learning about career opportunities at Amazon, my group has people in Germany. We have people all over Europe. Please feel free to contact me and I'd be happy to talk to you. All right, thank you very much.
Thank you, Larry. So, any question in the audience? So, just one quick question for me. How far are we from the virtual try-on that we can see on the market that works with a good precision?
All right, so Amazon released the first version of what I call this paper doll virtual try-on. It actually is available on some number of tens of thousands of items in the catalog, which sounds like a lot, but it's really a very small percentage of the catalog. I expect that a year from now, even though, I mean, you can go and you can try it out now if you can find one of the items that supports it. But a year from now, it should be pretty widespread. And I'm hoping that we'll be able to increase the number of product types that it supports also. That's really an important goal for us. All right. But I would say in about a year, it'll be much more widespread in the Amazon catalog.
Okay, thank you. Any question? In the audience, raise your hand eventually. So if not, let's thank once again our keynote speaker, Professor Larry Davis from Amazon.
Thank you very much, Casimir. I appreciate the
Thank you very,
opportunity to
thank you very much. Thank you, thank you.
Bye-bye.
Bye-bye, bye-bye. So let's skip to the next oral session chaired by Marco Leo. Okay, chaired by Antonino Furnari from University.